Hi everyone, this is Amantamal Sinha again, and I'm here with a walkthrough video for the CSE 331 project about problem 1. Now that you have enough background by watching both the background motivation video and the routing algorithm videos, if you haven't already, then please go check those out. In this video, we'll give an overview of problem 1 while also discussing the notions of revenues and penalties for this problem and beyond. So we've reduced the actual problem involving for profit only to a toy version, that is problem 1. Here, the constraint on the actual problem, the bandwidth value b sub u, is set to infinity. So effectively, this is not a concern while thinking of solutions. But clients are not so lenient, and the tolerance threshold, alpha c, the meaning of which will become clear later in this video, is set to 1. However, the infinitely high bandwidth b sub u values offset the stricter tolerance threshold alpha c values. Just a reminder, for this problem, your group needs to design paths around these constraints to maximize revenue for profit only. But first, we need to start by going over what revenues and penalties mean in the first place before we move on to problem 1, since these definitions will be relevant to other problems as well. Let's talk about revenues. We start with discussing this informally. The company for profit only gets some amount of revenue from each client C. After the routing simulator routes their packets, it outputs the routing delay for each client. Each client C also has the following parameters: tolerance threshold alpha C and the minimum path delay D of C. For client C, if the routing delay is less than or equal to the tolerance threshold times the minimum delay, then the revenue amount is the payment amount since the constraint is satisfied. That is, the routing delay is under or at the given constraints. On the other hand, if the routing delay is greater than the tolerance threshold times the minimum routing delay, then the constraints are not satisfied and for profit only does not get any revenue or the revenue amount from a client equals 0. We're going to go through an example for this definition in the next slide. Formally, we can define this on a case-by-case basis, where the revenue amount from a client, rev naught, is equal to the payment amount to be received from a client C, payment of C if the predicate is satisfied and is 0 if it's not. Let's walk through an example from the routing algorithm videos to get a better sense of this revenue concept. We have the graph and the table for the path keys. On the top right corner, we have a table with headers including the client C, the minimum path delay little d of C, the routing delay capital DP dash of C, the tolerance threshold alpha C, and so on. We will choose client 1. Client 1 has its routing delay capital DP dash of 1 equal to 2. Then we look at the minimum path delay of a client, little d of c. That is the minimum value out of the sum of delays of all the edges of all the possible I to C paths, p of c from I to c. In the case of client 1, we can see that the minimum path delay is 2. This is because if you start from node 0, the content provider node denoted by I, then we have the current path p dash of 1, the dotted line from node 0 through node 10 to node 1. But we can also go from 0 to 1 through node 9, then node 3 and 2, and then finally node 1. But that involves 4 edges and is going to have the path delay value equal to 4. Now it's easy to see that the minimum delay d of c for client 1 must equal 2. The tolerance threshold for client 1, alpha 1, is equal to 1. Then we see that the routing delay, capital D p dash of 1, equals 2, which is 2 times 1, or the minimum delay, little d of 1 times the tolerance threshold, alpha 1. So we have capital D p dash of 1 equal to alpha 1 times little d of 1. And if you look at the definition for revenue, then we see that this satisfies the first predicate. So the revenue amount from client 1, rev naught, equals payment of 1. Here we have the same example, but we're going to look at client 8. For client 8, the routing delay, capital DP dash of 8, equals 5, as we see on the table. Remember that these values have been worked out in the routing algorithm videos, and the minimum delay for client 8, little d of 8, is equal to 3. This is again because all the other paths involve more than 3 edges from node 0 to node 8. So again, we can see that the minimum path delay, little d of 8, is equal to 3 for client 8. Finally, the tolerance threshold for client 8, alpha 8, is equal to 1. This time, however, the routing delay for client 8, capital DP dash of 8, equals 5. But the minimum delay, little d of 8, times the tolerance threshold, alpha 8, equals 3 times 1, which is 3. So the routing delay, capital D P dash of 8, is 5 greater than 3, the tolerance threshold multiplied by the minimum path delay. So the first predicate is not satisfied, and thus the revenue amount received from client 8 is from the otherwise case, which is 0. We can interpret this as the path provided for client 8 being unable to satisfy the constraint and thus losing the payment or revenue amount from client 8. Now we move to penalties. The concept of penalties in this project is quite natural. It is the revenue amount from a client C minus the payment amount received from a client. And if we take the definition for the revenue amount, then that would imply that the penalties need to be defined in exactly the opposite manner in relation to the payments. So we flip the definition of revenues to get the following one for penalty pen not. If the routing delay of a client C, capital D P dash of C, is greater than the tolerance threshold alpha C times the minimum delay little d of C, then the path for that client P of C hasn't satisfied the constraints and the company is penalized by the amount equaling the payment amount to be received from that client C. On the other hand, if the routing delay capital D P dash of C is actually less than or equal to the tolerance threshold alpha C times the minimum delay little d of C, then the constraints are satisfied and there is no penalty to for profit only. Thus the penalty amount pen not is equal to 0. Again, we take the same example from the revenue examples to discuss penalties. We'll again start with client 1. Client 1 has its routing delay capital DP dash of 1 equal to 2. And we know that the minimum path delay little d of 1 is 2 as well. The tolerance threshold for client 1, alpha 1, is equal to 1. Now the routing delay capital D P dash of 1 equals 2, which is again 2 times 1, or the minimum delay little d of 1 times the tolerance threshold alpha 1. So we have capital D P dash of 1 equal to alpha 1 times little d of 1. And now if we look down the definition of penalties, the predicate is false and the penalty amount from client 1 is equal to 0. Next we look at client 8. Again, the routing delay capital DP dash of 8 is equal to 5. But the minimum path delay little d of 8 is 3. The tolerance threshold for client 8 is equal to 1. So the tolerance threshold times the minimum path delay is equal to 3. So the statement capital D P dash of C is greater than alpha C times D of C is true, and the penalty amount from client 8 is equal to its payment amount, or in other words, the paths didn't meet the given constraints and thus we are penalized. Finally, we'll formally define revenues by taking the formal definition of penalties. We do have a definition for revenue, but defining it this way makes sense for other problems as well. So formally, the revenue amount to be received from a client C is equal to the payment amount from a client payment of C, minus the penalty amount incurred by the client pen not. Now recall that the goal is always to maximize the revenue for profit only. So we also have to define total revenue. The total revenue is the sum total of revenues received from all clients C in the set of clients capital C. Now that we have rigorously defined revenues and penalties, we come back to problem 1. So the problem is to route packets from the content provider node I to each client C. In order to do this, you need to determine paths that the routing simulator can then use to transmit the packets for each client so that the paths satisfy the bandwidth B sub u constraint. Here, the bandwidth value B sub u for this problem is infinity for all routers U. The objective for generating these paths is to maximize total revenue for profit only while working under the tolerance threshold alpha C for each client C. In terms of inputs, we have the usual graph Z equals V comma E, with V as vertices representing the set of clients and routers and E representing the edges between them. Among the vertices, we have the content provider node 0, which we've denoted by I, and the subset C of V complement I representing the set of clients. In this graph, we have 1, 3, 6, 7, and 8 as clients. Now we also have bandwidth values B sub u for each router U and V. The bandwidth values are set to infinity for all nodes for problem 1. We also have the tolerance threshold for each client in C, alpha C, equal to 1. Finally, the priority value for each client C, priority of C, is set to priority default, which is equal to 0. So if you look at the priority table, for client 1, the priority value is 0. In terms of output, we have the list of paths p dash of c from the content provider node 0 to each client c. For problem 1, the important parameters are the bandwidth value set to infinity, the tolerance threshold set to 1, and the priority value set to 0. The output for this problem is the list of paths for each client from the content provider node I to the client itself. We can put this formally as the list LP dash of paths P dash of C for all clients C in the set of clients capital C. While outputting these paths, the objective for your group is for these paths to maximize total revenue for profit only. Now we go over a valid solution for problem 1, example 1. We have the graph with the content provider node 0 denoted by I and the other routers and clients 1, 3, 6, 7, and 8. There is the orange square shaped time ticker on the top left corner, and we have the diamond shaped packets for each client, whose colors match the colors of their intended clients. For example, client 1 is gray in color and its packet is also gray in color. We also have the path key and priority tables. For example, the path for client 1, p dash of 1 is the one represented in the first row of the path key table with a dotted line. In the graph, it starts from node 0 and continues to node 10 and then to node 1. In the priority table, we can see that client 1 has priority value 0. For each router U, we also see that the bandwidth value B sub U is equal to infinity, and the tolerance threshold for each client is equal to 1. What we also have here is a table that contains each client, the current node that their packets are at, and the routing delay for each client. Initially, since all the packets are at the content provider node, the current node is 0 for all the clients. Since this is the first iteration, the packet delay is 0. And since the packets haven't reached their destinations yet, the routing delays haven't been determined. Lastly, there's also a table that contains the minimum path delay for each client. For example, for client 1, the minimum delay little d of 1 is equal to 2. Now how the simulator works here is similar to the algorithm idea video for the routing algorithm. We start at time tick 0 and all the packets are at node 0. And since the bandwidth value b sub 0 is infinity greater than 5, the number of packets to be transmitted, the packets are forwarded to their next location and we proceed to the next time tick. Here, the packets have followed their respective paths and the table has also been updated. Again, if we look at nodes 9 and 10, then both have bandwidth values equal to infinity. So for node 10, that is bigger than 2, and for node 9, that is bigger than 3, the number of packets to be transmitted at each node. So we move to the next iteration. We're at time tick 2 and the packets for all the clients have followed their respective paths. Let's focus on the packet for client 3. The packet is at node 3, which is its destination, and this is reflected by its current position being updated to 3. Here, as in other iterations, the algorithm checks if a packet has reached its destination, and since the packets for clients 1 and 3 have, the routing delays for these clients are set to the current time tick, which is 2. We again see that the bandwidth values are set to infinity for both nodes 1 and 3, and we proceed to the next iteration. At time tick 3, we look at nodes 6, 8, and 4. For nodes 6 and 8, the packets have just reached their destinations, so the routing delays are set accordingly to 3. At node 4, the bandwidth value again is infinity, so the bandwidth b sub 4 is sufficient, and so the packet is forwarded along its respective path to node 7. At time tick 4, we see that the packet for client 7 has reached its destination, so the routing delay for client 7 is equal to 4. Notice the minimum path delays on the bottom right table for each client equal the routing delays on the top right table. For example, for client 1, the minimum path delay little d of 1 equals 2, which is because the path p dash of 1 involves two edges, 0 to 10 and 10 to 1. And so is the routing delay, which is equal to 2. That is, it took the routing simulator 2 time ticks to route the packet for client 1 from node 0 to node 1. Similarly, we have the path delay for client 8 equal to the routing delay, that is 3. So for all the clients, we notice that the routing delays are equal to the minimum path delays. And in a sense, we can say that the routing delay was minimized, and that is because of the bandwidth values being set to infinity. As we saw through the run of the simulator, no packets were delayed. Now we examine the penalties for each client C. Here we have a table with headers client C, Their minimum path delays, little d of c, the routing delays, capital D p dash of c, the tolerance threshold alpha c, the tolerance threshold alpha c times the minimum path delay, little d of c, the predicate for the penalty definition, whether capital D p dash of c is greater than alpha c times little d of c, and finally the penalty amount pen not. Let's start with client 1. The minimum path delay for client 1, little d of 1, is equal to 2. And as we saw on the last slide, the routing delay, capital D p dash of 1, also equals 2. The tolerance threshold, alpha c, is equal to 1 as for all the clients. So the product of the tolerance threshold times the minimum delay is equal to 2 as well. And the predicate for examining penalties, whether the routing delay capital D p dash of c is greater than the tolerance threshold alpha c times the minimum path delay little d of c, is false, since they are actually equal. Finally, as we see from the definition below, the penalty for client 1 is equal to 0. Similarly, for all the clients, we have the following values. As discussed in the last slide, each client's routing delay is equal to its minimum delay, and since the tolerance threshold is equal to 1, the predicate is always false, and hence the penalty amount for each client equals 0. Now we look at the revenues for each client. For all the clients, we have the values from the last slide. Recall the formal definition of revenue, which is payment minus penalty. Since the penalty amount for each client is 0, the revenue amount for each client is equal to the payment amount, payment of C. Lastly, we look at the total revenue for profit only. The definition is simply the sum of revenues received for each client. The revenues for all the clients, as worked out in the previous slide, is equal to the respective payment amounts. Let's take a look at the payment amount, payment of C column for each client. For client 1, it's $30, and for 3, it's $40. Similarly, for clients 6, 7, and 8, the payment amounts, payment of C, are $35, $40, and $45 respectively, and this gives us the value $190. This is because we added all the payment amounts for all the clients to get $190. And this is the maximum possible revenue for profit only. We want to leave you with a hint. The optimal solution for this problem is similar to a homework problem that y'all have already seen in this course. As always, thanks for watching.